What if internal combustion engines were 100% efficient? What if a 250 cc motorcycle had zero energy loss? Join us as we dive into a fascinating thought experiment to calculate the mind-boggling mileage of such a machine, even considering real-world environmental factors like air resistance and rolling friction. You won't believe the numbers. Have you ever looked at your motorcycle's fuel gauge and wished for just more? More miles, more freedom, less stopping at the pump? Well, today, we're not just wishing. We are asking one of the biggest what-if questions in engineering. What if a 250 cc motorcycle engine was, for lack of a better word, perfect? We're talking 100% combustion, zero energy loss. A dream engine. How many kilometers or miles could you squeeze out of a single liter of fuel? The answer, even with real-world factors, might just blow your mind. Let's start with reality. The engines in our bikes today, as incredible as they are far from perfect. When you put a liter of gasoline into your tank, only a fraction of its chemical energy actually translates into power pushing you forward. The vast majority, sometimes up to 70%, is lost as heat. Heat that goes out the exhaust pipe, heat that your cooling system has to dissipate. Then there's friction within the engine itself, pistons rubbing, bearings turning, pumps moving fluids. These are all energy losses, silently eating away at your fuel efficiency. So when we say a perfect engine, we're talking about an engine where every single joule of energy in that gasoline is converted directly into mechanical power. No heat loss, no friction loss. Sounds like science fiction, right? It is, but it's a fun thought experiment. To appreciate the perfect engine, let's establish a baseline. A typical modern 250 cc motorcycle, ridden reasonably, might get you somewhere in the ballpark of 30 TO45 kilometers per liter. That's roughly 70 TO105 miles per gallon. Let's take a good average, say 35 km per liter. Now, if we assume that this 35 km per liter is achieved with an engine operating at, say, 30% efficiency, a respectable figure for a modern bike. If we just fix the engine to 100% efficiency, without considering anything else, we'd simply multiply that current mileage by the inverse of the efficiency. So 35 km per liter multiplied by 100% 30%, or roughly 3.33. That alone gives us a theoretical 116 kilometers per liter. That's already mind-boggling, over 3 times the range. But that's not the full story, because that calculation still doesn't account for the world outside the engine. This is where things get interesting. Even with a perfect engine, you can't escape physics. The motorcycle still has to move through the real world, and that world pushes back. First, and arguably the biggest factor, is aerodynamic drag or air resistance. As you ride, you're constantly pushing a wall of air out of your way. This force increases dramatically, not linearly, but with the square of your speed. Go twice as fast, and you're fighting 4 times the air resistance. This is why highway mileage is often worse than city mileage, even for perfectly efficient electric vehicles. Second, we have rolling resistance. This is the friction between your tires and the road, and friction within your wheel bearings. It's a less dramatic factor than air drag, but it's always there, working against you, slightly increasing with speed and the weight of the bike and rider. And finally, drivetrain loss. Even with a perfect engine, you still have a chain or belt, gears in the transmission. These mechanical components have their own inherent friction, eating up a small percentage, perhaps 2% to 5% of the power, before it even reaches your wheel. So a perfectly efficient engine still has to generate enough power to overcome these external forces. To get the absolute maximum mileage, we need to consider the sweet spot where these resistances are minimal. This usually means a low steady cruising speed, where air resistance hasn't become dominant yet. Let's pick a hypothetical optimal speed of 40 km per hour, about 25 mph. At this speed, a 250 cc motorcycle and rider would need a certain amount of power at the wheel to maintain it. Let's estimate this at around 1.2 kilowatts. This is the power needed to overcome the air and rolling resistance combined. Now, because our engine is 100% efficient and our drivetrain is highly efficient, let's say 98%, the amount of chemical energy we need to pull from the fuel is just a tiny bit more than that 1.2 kW. Gasoline holds an incredible amount of energy, about 32 megajoules per liter. 1 kilowatt-hour is 3.6 megajoules. So 1 liter of fuel contains enough energy to provide 32 mJ. 3.6 mJ per kilowatt-hour equals 8.89 kWh of perfect, usable power. If we need 1.2 kW of power, and we have 8.89 kWh per liter, we'd be consuming roughly 0.135 text-liters of fuel per hour to maintain that 40 text km/h speed. And that gives us a staggering theoretical mileage of around 296 text kilometers per liter, almost 300 kilometers per liter. Think about that for a moment. 300 text km/liter. If your bike has a 10 text minus liter tank, that's a range of 3000 kilometers on a single tank. You could ride from Paris to Rome or across half the United States without refueling. This isn't just about saving money, it's about unparalleled freedom, radically reduced emissions, and a fundamental shift in how we power transportation. Imagine a world where 250 cc bikes are more fuel efficient than any electric car currently on the market when comparing range per unit of energy. Of course, a truly 100% efficient engine is impossible due to the laws of thermodynamics. There will always be some energy lost as heat. But this thought experiment highlights just how much room for improvement there is and how much energy we currently waste in our efforts to move around. So if the payoff is this huge, why don't we have these engines? Well, as mentioned, the laws of physics are pretty firm. The Carnot cycle limits the maximum theoretical efficiency of any heat engine. We're constantly working to get closer to that theoretical limit, but 100% is simply not achievable for a heat engine. Engineers are making incredible strides with new materials, advanced combustion techniques like homogeneous charge compression ignition, HCCI, and improved thermal management. But every percentage point of efficiency gain is incredibly hard-won, requiring immense research and development. This is also why we see such a strong push towards electric vehicles, which can achieve much higher overall efficiencies from energy source to wheel by avoiding the combustion process entirely. So there you have it. A 250 cc motorcycle with a perfect 100% efficient engine, even when battling the elements, could realistically deliver close to 300 text kilometers per liter. A truly impossible mile, but a fascinating glimpse into the potential that's locked away in every drop of fuel. What do you think? Could you imagine riding a bike with that kind of range? Let me know in the comments below. Don't forget to like this video, share it with your fellow riders, and subscribe for more mind-bending automotive experiments. Thanks for watching, and I'll see you in the next one.